Good afternoon, everyone. I have to talk to you in English because Nick will be listening me. I don't want him to guess what I'm saying against him, so I have to be fair and square and talk to him. I have known Nick for quite some time through various conferences we organized together, and we are, I think, good friends with him, right?
Definitely.
He's a
Katılımcılarımız ikinci kat F121 nolu sınıftan Microsoft atölyesi düzenlenecek.
Microsoft is
Sertifika verilecek.
organizing a
Katılımlarınızı bekleriz.
meeting, so that's why they are announcing it. Anyway, Nick has been working in various jobs. He was a MSA Microsoft Research Asia member, senior member, and then came back to Cambridge. He worked there, and then now he is.
Değerli katılımcılarımız,
Can you tell them
ikinci
to
kat
shut up?
F121 nolu sınıftan Microsoft atölyesi düzenlenecek. Atölyede sertifika verilecektir. Katılımlarınızı bekleriz. Saat 2'de.
Anyway, let us get back. He is now working as a full professor at Cambridge University. I'm sure everyone knows Cambridge University, one of the top universities, not in UK, but in the world. And he is also the founding member of the Flower Labs, which has federated learning environment. They developed an open source software called Federated Learning, and they are doing great things. I will post more information about him, and if you are interested, we can talk too. Anyway, I won't take much of your time and his time as well. He just squeezed this talk between his busy schedule. So thanks, Nick, and take it away.
Thank you much for the kind introduction. I just need to share my screen, and it says that the sharing is disabled right now.
Sharing'i açar mısın? Paylaşım, ekran paylaşımı. Okay, Nick, you can share your screen now.
Great. 1 second. Let me do this.
Yeah.
Just need to
Okay.
straighten up the view. 1 second. Okay, great. We can get underway. Thank you so much for the very kind introduction and the invitation to be here. What I want to talk to you about in the next 25 minutes is a passion that I have towards the world, all of us, starting to think about decentralized forms of machine learning. I think this is a really important issue for us to tackle in the next 5 to 10 years because it really, if we can migrate from what is currently a very centralized approach to doing machine learning, I believe that by moving to decentralized, we can have a much greater enfranchisement moving forward. Let me first tell you about how I see the world right now in terms of machine learning and data centers, and then I'll move on to where I think we can perhaps get to in a number of years. So let me begin by being clear about what I'm talking about here. When I'm talking about the current state of affairs, it looks something like this. And so the way that we build all of our machine learning today is heavily premised on the use of data centers that are centralized. And so it doesn't matter what type of machine learning you happen to be involved in. If you're using machine learning that exists on your smartphone, if you happen to be using machine learning that is built inside things like Netflix, if you happen to be searching any sort of Google query and looking for some pictures, all of these types of machine learning are trained and built and then deployed, largely speaking, in the same way. And that is that they use data centers, as illustrated in the middle here. They use many thousands of GPUs, and then the data that drives these models are centralized too. And so these are carefully curated, relatively large data sets used to train these models. And so this is the paradigm that you can't escape from right now. The trouble with this situation is that it has a large number of sort of foundational limitations that we're not going to be able to address if we remain in this current situation. So let me illustrate some of these strong limitations. So one limitation, one real strong thing that we have to be all concerned about is that in this data center approach, there's a lack of user privacy and control, because it fundamentally requires you to copy data into the data center before you can do the training. And so as data has to leave the hands of the user or various organizations and be copied into this sort of infrastructure, when that happens, as soon as it happens, you've lost control. You basically have to assume a good actor is going to use this data fairly and for the purposes that they originally acquired it. But that can be very hard to enforce. You're not sure how the data is going to be used, and so this is a key issue that everyone is sort of worried about right now. But I want to also emphasize there are a number of other issues. So one of these issues is that systems we build on top of models, there could be the systems such as robots, there could be systems such as smart devices, such as illustrated here, like a smart stethoscope that's analyzing information. And there are many examples of devices that we're trying to embed intelligence into. Whenever we do this, if we are placing the intelligence within the data center, which is common today, then that system, that device, that robot is very fragile. As soon as the data connection drops or becomes slower, that the smart device or the robot or the decision that needs to be made may not be possible at all, or it may happen much slower than it needs to happen. And so again, this is a fundamental issue with architecting the machine learning in the data center. There's also issues to do with energy and carbon footprint. It's been realized now for a number of years that the training of these models, while they do produce incredibly strong, interesting algorithms, they require us to use a lot of energy and a lot of carbon. And so, recent calculations have shown that the best NLP models available today, when you add in all the bells and whistles of the various kinds of techniques and so on, and using AutoML, all the things that are necessary to have a state-of-the-art model, often means that training that even just one model of these kinds can use huge amounts of energy and have a huge carbon footprint. And so the one illustration here is an example, and it denotes that around 5 cars driven for their whole lifetime is the equivalent carbon footprint of training one state-of-the-art model. Another chief concern that I have, that I don't hear being spoken about that much, is the use of this data. And so fundamentally, if you're copying data into a data center before you can embed it inside a machine model, then that process will lead you to have data sets that are carefully curated, but are actually relatively small relative to the big diversity in the world. Because if you have to copy data over, carefully tidy it before you can train on it, you're always going to have this issue where that data is going to be quite separate from all the messy data that exists in the real world. And so for this reason, models that are trained in this way are often quite biased, simply because the data, even though it can be relatively large, is unable to capture the full breadth of complexity, of different demographics, of different locations, ways things to look and feel. It's unable to capture all of that accurately, and so that means that the model is going to have to be biased. And so this is an issue that's going to be very hard for us to overcome unless we start to train on different types of data. And so for these reasons and many more that we could discuss, I think it's time for us to really carefully start to invest a lot more energy and money and folks thinking very carefully about two important characteristics in all of the algorithms we invent going forward. And that is, they need to be decentralized, in my opinion, and collaborative in nature. And so this illustration here on the right-hand side of the screen, it tries to point out a future view of the world whereby the algorithms that are built no longer are centralized by first principles, but they are assumed to work in a decentralized manner where they're going to be run independently from each other by different organizations, some of those academic, some of those run by different governments, some by different companies, and they're designed in a way that they can work together. And this is something that is almost never apparent and available in the machine learning world of today, but it's a desired outcome that I think we need to strive for. And so if we can make this leap into building algorithms where we are allowing people to train parts of the model on the data they have independently from each other, allowing folks to truly work together in a real collaborative fashion, then we can have really big transformative effects, I believe. And so the types of benefits that I see that we could accrue if we could study these methods and start to make them operational are ones such as the following. Resource sharing is a big one. Right now, because of the centralized approach, you need to bring together all of these resources before you can train a large model. But if we could have true decentralized training, whenever we need to build a different model of different sizes, of different capacity, different scales, we can do what normally happens in the rest of computer science, and that is, on demand, bring upon the resources that you need, because those resources are networked. It's a very common idea that it is very common in other types of computer science, but is currently absent in almost all of the dialogue to do with machine learning. We also have a much better ability to control privacy, because if a user, an organization decides they no longer want to have their data used in a particular way, well, then they can opt out. And there's also a lot of reasons, like won't dive into now, why this type of design would allow systems that are much more compatible with emerging AI regulation. And so those are some of the more granular reasons why, but there's two other reasons I really want to dive into to explain why I think building and inventing methods of this kind is so important. And so one of these is to do with the data opportunity. So the data opportunity that I see is most of the data that is trained in machine learning right now is called large. But it's really large only from the perspective of what data was used previously to train models. In fact, all the data that's being used to train these amazing models, such as ChatGPT or other foundation models and so on, is often just used and found on the internet. So this is easily accessible network data. It may be relatively large, but if you think about all the data in the world that's not on the internet, that's not available on the web, it's actually enormous. You can think of all the data in people's PCs, all the data in people's phones, all the data that happens to be in factories, in factory lines, or in enterprises, or in organizations where the data is very sensitive, and so there's an anxiety about sharing it. If you look at all that data, and we call it something else, if we call it distributed and sensitive data, that data is hugely much larger than the centralized machine learning data that we use right now. And something that we've learned over the years, if nothing else, whenever you can add more data to these models, they fundamentally become better. And so one very strong fundamental reason, beyond the ones I just described also, that we need to pivot and move towards decentralized methods is that the amount of data that's currently untapped is extraordinary and is currently unavailable to methods that are centralized by nature. So I call this the data opportunity. The second opportunity that I want to explain is that of the compute opportunity. And so right now, the only way you can train a large model is to, as I said a number of times now, is centralize and gather a large number of GPUs all together. And so if we look at the types of data centers that people are building right now, they look something like this. So right now, it'll cost you about $800 million, US dollars, to collect together around 22,000 NVIDIA H100s. And this represents a common investment being made by large businesses today. When you add up all the floating point operations of those 22,000 GPUs, they add up to around 2.9 exaflops, so a huge amount of compute. But what is interesting is that there's a vast amount of compute in the world today that is currently not being used at all for machine learning. Even though machine learning requires fundamentally a lot of compute to train these models, we are ignoring large fragments of the computation already in the environment. And so let me give you one example. This is just an illustrative example of how many exaflops is currently available in the hands of many people. And so the example I'll give you is a about 2 years ago, Samsung sold only one type of phone. So if we look at their flagship phone, the most expensive phone, they sold around 20 million of these. Each of those phones were embedded with a Qualcomm Snapdragon chip. And if you add up all the floating point operations that those 20 million devices could execute, we actually get to a huge number, 70 exaflops. And so what I'm trying to do here is illustrate on the left-hand side, this is a very expensive data center that's being purchased and deployed by individual companies to train these models. And when you add up all the floating point operations that sort of unit can do, it's quite impressive. It's around 3 exaflops. But if I just arbitrarily pick a collection of devices, this is just one category of phone sold in 1 year, it actually adds up to a huge, much larger number. And those flops right now are not being used. And so we could think of many different other types of devices out there. Some would be stuck in enterprises on the PCs. Some would be in small data centers that are not networked together. There are many examples where we can see much larger amounts of compute that are completely not being used at all for machine learning today. And yet we know that computation is a critical, perhaps the second most critical ingredient to doing good machine learning. And so the way that we can access this data and the way that we can access this compute is only by starting to invent different types of decentralized machine learning. And so that brings me to say, well, if we want to have this vision, I want to be transparent and say the types of algorithms I'm talking about right now are not well understood. There's not many examples of them, but I'm saying there's a large number of advantages for us to be able to get there in time. And so naturally, one question is, how do we get there? How do we make that first step? Because I'm certain that this will take a long time to invent these algorithms, and a lot of investment is required of people's minds and many students and many faculty, many companies and so on. But there always needs to be a first step. And so the first step that I'd point to is what I've been spending a lot of time lately on, and that's a slightly more constrained form of the same idea. And this is the idea of federated learning. And so I believe that federated learning, it's a well-known existing concept, doesn't have all the characteristics that we need, but it has many desirable ones already. And we can use this as a gateway to become and reach into this decentralized and collaborative sort of platform. And so for those of you who haven't seen federated learning before, it looks something like this. I'll give you a 1-minute introduction. And the whole idea of federated learning is that what we do is that we see where the data is that we want to train on. They might be on a various number of phones, or that might be in a number of different PCs in an enterprise environment. And instead of moving the data from those devices or from those PCs or wherever the data happens to be, instead of moving the data to a data center, we actually and we perform some local computation on that data independently of each other. And that's what this animation is showing you here. It's showing you data existing in 3 different devices, and rather than copying the data to one central place, small amounts of training is performed, and then the units of computation, the small learnings are then aggregated, not the data itself. The small learnings are then merged together to create a model. And so this can be, a gateway for us to be able to start to do this type of work. So examples of federated learning include Android keyboard. Hospitals are starting to prototype these things. But what's fascinating is about this technique that's been around for a while. What's fascinating about it is that it's not used right now for any of these breakthrough methods that we see. ChatGPT was not trained with federated learning. All those OpenAI, all those models from Google, all those models from Amazon that we hear about are not using federated learning. And so for that reason, we started to look at what are the hurdles that are needed to be overcome so we could see much more pervasive use of federated methods. And then ultimately what I'm thinking is that we can use this as a gateway to us moving towards even more aggressively decentralized methods in the future. Let me tell you about one sort of fundamental idea we have here. This is a laundry list of methods that you'll typically hear from academics as to why we're not using federated right now. They say things like, oh, well, there's challenges to do with non-IDness, there's challenges to do with scalability. But what I think is the critical bottleneck is that it's overly complex and limited in terms of the tooling that we have. In my view, right now, what we sit in is that we we basically are in the same situation that deep learning was about 12 years ago, where if you wanted to train a model, you had to do an awful lot of heavy lifting yourself and code a lot before you could even train that model. So I believe, though, if we could do the same thing for deep learning, which is introduce frameworks like PyTorch and TensorFlow that made it open and accessible to all, so they could start to train their own models and experiment with this space, then we could actually see sort of a proliferation of people doing federated learning. And so I think it could look something like this. Right now, if you could grab anyone off the street, you can give them PyTorch and they can train on 1,000 GPUs without even thinking about it. In the future, what we need to do for federated learning to become more mainstream is do the exact same thing by introducing a piece of software that would allow anybody, a data scientist, a student, someone working in a company, to train on 1,000 different data sources and not even think about it, the same way they don't think about it today in terms of GPUs. And so for that reason, we've started working with a community, an open source community, developing a tool called Flower that we want to able to occupy the space to enable many people to start jumping into this, what is currently a difficult to enter space. We already have a lot of contributors, a lot of traction of people using, but I want to emphasize that this is an open source and community effort towards building a tool for everyone to use so that we can accelerate the process of us perfecting decentralized machine learning methods. I wanted to share with you in the last part of this talk something that I think is really interesting. And so one thing I hear from people when I talk to them about federated learning and decentralized methods is that they say to me, oh, well, it's not ready for prime time. We can't really train these big models. So why, is it really any use? And so I'm excited to say that we've developed our very first example of what I think to be a milestone for federated learning. And so that is a method called Flower LLM. And it's an example of the world's first 1.3 billion parameter LLM that was actually pre-trained. So that means trained from scratch using federated learning. And so I think then, the main sort of characteristics of this technique that makes it so exciting is that it enables people to use federated learning to train an LLM. And so you can train these large models. In this case, we've showed that for the first time, you can train a model that's 1.3 billion parameters. And we're doing it by combining different GPUs around the world and combining different data sources, again, split around the world. And so the main reason why this is so exciting is that you can imagine people using this type of recipe to compete and to do the types of techniques that we see the big companies doing by bringing their own individual resource together. Not only this, if we can imagine people being able to combine resources together, we also believe this can lead in time to even stronger, more powerful forms of LLMs. And so the main reason we've done this is to show people that federated learning is not isolated to small different types of models you might find in phones, but you can apply the same techniques with a bit of heavy lifting and a lot of work, I've got to say, but you can apply these techniques to even the largest models that we know today. And so Flower LLM is really a breakthrough, I think, because it's a threefold increase in the terms of the size of model that we've shown that you can train. The nearest piece of work that we're familiar with is from Google DeepMind, and they showed you could train around a 400 million parameter model. But we've developed a series of methods that allow you to go through this 1 billion parameter sort of ceiling to 1.3 billion parameters. And now you can really start to say that this is a true foundation model. But let me just tell you a little bit about the comparisons. And so using this technique, we've used Flower to show you can train models of this size. And so this is a comparison between the number of parameters and other sort of key performance characteristics about this technique. So on the far right-hand side, you can see the technique from DeepMind. So they maxed out at around 400 million parameters. We've shown, they used for this around 16 GPUs and so on. We've shown under different variations of the same recipe that you can go up to 1.3 billion. But you can also have, for example, on smaller scale parameters, you can have even a larger number of clients being used. We think the same techniques can be used to scale up to around 30 billion parameters. And that's what we're going to be doing over the next 12 months. So we've released a 1.3 billion parameter model. We've shown it's possible. The next steps will be looking at 3 billion, 7 billion. And we think in time, we'll be able to go up to 30 billion using the same techniques that were developed so far. So that's the kind of sort of example I want to show you to sort of really illustrate that this technology, this step, is ready for being used in the federated context. And I'm happy to take a few questions from the audience. Thank you so much for giving me the chance to talk to you today and tell you about why I think decentralized methods are going to be so important.
Thanks, Nick. I have one simple question. One of the maps, the world map you showed, Turkey.
Yes.
One previous one. Go back.
Oh, yes. Yeah, like this. Let me find it. 1 second. Yeah, here.
There is something in Turkey. Is that what it is?
Yeah, this is a real map. This is real data from users who are using Flower. Okay. So yeah, there must be some users. We should find them.
Yeah. That's what I will check. Yeah, thank you. Anyone else? Yeah.
Mikrofonu götürebilir misiniz?
Tabii.
Hi, Nick. Thank you for the presentation. It was great. I live in Bournemouth,
sure,
by the way. Anyway,
right.
just wanted to ask you if these federated systems that you have applied could be using the blockchain vis-a-vis the ESG movement that is moving. I'm working on a startup, so very interested about this new ventures you're on.
Yeah, so we've had quite a few people interested in how you could use the technology combined with blockchain. We ourselves haven't built any sort of blockchain aspects to the techniques so far, but I think the potential is quite high. And so I believe there was a company called Flock.io looking into this. But no, we're happy to talk to you later perhaps about how it would be combined. I think it could be a very important step, I think. So people could, one part of this it would be allowing people to attest to the work that has been done and verify the work has been done correctly.
Yeah,
that'd be an important part of it, I imagine.
I was looking for a blockchain that does centralized and decentralized for the raw data analysis. So that will be interesting to see where you guys stand in that, and maybe there is a company that you guys are willing to work with. It'll be really interesting to hear from you. So I'll get in touch. Thank you. Cheers, mate.
Sure, it's completely open source. So it's a complete open source. We always love people, building different parts of it. It's great.
Cheers, Nick.
Thanks.
Hello, and thank you for all info. As one of a guy here asked about using, I was more interested in security part in this model you are using. And as I got it wrong, you said we are using the same method like blockchain. Am I right?
We're not using blockchain.
Also, so can you give some information about the security part? Because as you talk about the distributed method, so for example, even I can use my or my friend resources and join to this community. But how we can get sure about the security part about our data in this model?
Oh, I see. Well, what we've built so far is assuming everyone is a good actor. And so anyone can use the software to build these networks.
Yes.
But we haven't built any part of this system yet that would allow people to verify what's being done is actually what's being done.
Yeah.
The code is all open source, so you can actually see the code that's executing on your machine, no problem. But this is really like a platform for people to build systems that do that type of thing. This is it's not being built so far to be a turnkey distributed system for training. It would allow people who are interested in that way to build those systems, if you know what I mean. It's the same way as PyTorch. PyTorch doesn't tell you necessarily about what the model is going to do, or it doesn't sort of make any guarantees about the computation that's being done. It just provides you with a tool to do this sort of thing. But I think it would be great for people to build these sort of complementary pieces alongside it.
Okay, there is no common model for that. Everyone should have their method or use, as you said, this is the open source. So we should find our method to secure our data.
Yes, so imagine if somebody really wanted to build a sort of a decentralized way of training and they want to work with people who they don't know. Because basically there are two models, right? More than two models, but the two extreme models. One is where people know each other and they just want to be able to train these models together. And that's what I would say we've been enabling. But then if you want to work with people you do not know, well then that raises the stakes a lot more. And so the systems that you could build right now with the tools that we have are more to do with people who already are known to each other and they just want to collaborate. So it could be academics, it could be networks of hospitals that already know each other and so forth. It's not meant to be, it would be unwise to use the software as it is if you're working with folks that you don't know. You would need to put in additional methods to attest to this. And so we actually have been working with folks like Intel and NVIDIA to support some of their built-in hardware security, but that's not really ready yet.
Okay, thank you.
Sure.
Okay, what Professor Rashid, I don't think they heard you, but if you have any other questions, you can email Professor Rashid from the AI department in BAU so that he can pass your questions to Professor Nick Lane. I would like to thank you, Professor
Thank you,
Nick Lane,
Nick.
for the gorgeous
See you
speech.
in a month.
Yeah, sure. Sounds great. Yeah, take care.
Thanks. You too. Bye-bye.